This is a rotational shear interferometer. Light comes in on this path, goes to a fold mirror here and a fold mirror here. The relative angle of the fold mirrors can be adjusted with this rotation stage. The relative time delay between the two paths can be adjusted by translating this stage. Here we're going to measure the field coming from the two paths. We might have one path inverted along the x-axis, the other path inverted along the y-axis. This creates a net inversion through the origin that allows us to characterize the mutual coherence as a function of spatial separation and temporal delay. And we'll talk about how we use these kind of devices to characterize coherence functions in today's episode. Computational imaging. Episode 43, two-beam interferometry. Now, in the last episode, episode 42, we talked about how to propagate coherence functions from one plane to another. And we found that we could take a simple Fourier transform in the case of Fresnel diffraction to describe the coherence function generated by an incoherent source on a remote plane. But we were analyzing in that case, for example, the sun. And as you know, if you look at sunlight on the surface of the Earth, you don't see coherence. What you see is a constant broad illumination from the sun. To analyze the coherence, you need to do some kind of interferometry, which we did simply in the last episode by looking at sunlight, for example, reflected off of a fingernail, where we saw a little bit of an interference effect. To be more systematic about it, you might just build a interferometer that takes pairs of points and directly measures their mutual coherence. And that's what's done here, for example, with a Michelson interferometer. This, of course, is the same device as we used to analyze wavefronts in Chapter 5. We talked about phase retrieval, but here we're using it to look at fields which have many temporal modes and many spatial modes potentially. And so we'd have to think about more complicated interferometers. But in the simplest case, we just have these two mirrors. And so the input signal comes in here, gets split on two paths and recombined with some path delay delta. Now, the field, if we assume only a single spatial mode, consists of the field at time t and then the field with this temporal delay. The self-interference of these two terms both measure gamma of 0, because we don't care about the absolute time of the field, we just care about the relative time delay. So each of these has a 0 time delay when it interferes with itself, but when E of t interferes with E of t plus delta, we get gamma of 2 delta over c, because it's gone twice over the path delay on the two paths, and gamma of minus 2 delta over c. We know from the Wiener-Caccini theorem that if we take the Fourier transform of the mutual intensity or the mutual coherence, what we get is the spectrum of the field. So the Fourier transform of this interference as a function of delta would allow us to reconstruct the spectrum of the field. Spectra come in many different shapes, of course. We had a monochromatic beam. It has only a single frequency. So its spectrum would be a delta function, and its mutual coherence would be a harmonic function. This is a Gaussian spectral envelope, and it has this mutual coherence and this spectrum. So a Gaussian envelope on the spectrum. The Lorentzian spectrum has this kind of shape. And so if we look at these kinds of spectra, what you see on the left is the spectral density, on the right is the mutual coherence. Now, this is not really what the mutual coherence looks like when you measure it. This is the envelope of the mutual coherence. Now, the frequency here is shown at some center frequency, which at optical frequencies, the center frequency would be hundreds of terahertz, and we're showing the bandwidth around that center frequency. When we actually measure the mutual coherence, this is what it would look like. So it will oscillate very quickly with a frequency proportional to the wavelength. So as we delay by each wavelength, we'll see fringes come in and out of phase. And so if you build this instrument, a Michelson interferometer with a spectral field coming in, what you see is these interference fringes and the extent of the fringes as a function of delay. Here it's shown in microns, but it can be expressed in terms of the bandwidth of the field or the coherence time, and the coherence time will be inversely proportional to the bandwidth. So as the spectrum gets narrower, these fringes would extend for further and further. For a monochromatic source, you'd see fringes for any path delay, but the envelope corresponds to the spectrum. So this is, of course, the principle that underlies Fourier transform spectrometers. This course is not a course in spectroscopy. We're interested in imaging. So we're interested in systems that contain many spatial modes. We want to measure the spatial coherence. One way to do that, for example, would be to use this 2 points in space and just watch them interfere spatially. This is the underlying principle behind the Young's double slit experiment. And you see interference functions that are laid out. Here is a function of the relative coherence of these 2 points in space, and we could go choose points in space in pairs and measure the interference between each pair and figure out their mutual coherence as a function of the delay. In this case, the fringes appear because the path delay from P1 and P2 is different for different points on the field. But we're usually interested in measuring this in a more systematic way. And we're most interested typically in looking at fields generated by incoherent sources. Back in episode 42, we derived these equations where the mutual or the cross-spectral density on the diffracted plane is related to the power spectral density on the input plane of an incoherent source by this transformation, which under the Fresnel approximation becomes a Fourier transform kernel with the Fourier transform variable u is equal to this delta x over lambda z. Okay, so the important point here is that if we neglect this q factor, which describes a phase delay as a function of z, w is only a function of delta x and delta y. So the cross-spectral density is stationary on the diffracted plane. What that means is that w is not really the four-dimensional function w of x1 prime, x2 prime, y1 prime, y2 prime. It's really a function of just these two variables, delta x and delta y. So in many cases, we only have to measure w for different separations in the plane. That's why you see radio telescopes laid out like this. This is a picture of the Very Large Array in New Mexico, where you see these radio telescopes laid out in an array, and this is built as a correlator so that the field is measured at from different antennas and then correlated between those antennas to measure the cross-spectral density. The VL8 is laid out in that format because when you lay antennas out in a Y, you can choose any pair of antennas and get a different value of delta x and delta y for the separation between those two. Now with a radio telescope, you can record the actual field and then computationally find the correlation between the fields. With optical frequencies, it's not possible to capture the field with an antenna. We only get one measurement per detector element, and so we need a different kind of instrument. There are many, many different kinds of instruments that are used for interferometry. We'll talk about some of them later in the course. Mostly, though, we're going to talk about simple systems using lenses, although we'll talk later about some Mach-Zehnder strategies for measuring coherence. But today I wanted to show you just the simplest way to make a two-dimensional measurement of W of delta X, delta Y, and that uses something called this rotational shear interferometer that we talked about in the introduction. So we have an input field that comes in here. Let's say it's got this X and Y. If we fold it along one path, we can turn X into minus X, and the other path we might fold and turn X into Y into minus Y. This inverts the field. Now, those mirrors can be rotated at various angles to change the scale of this inversion, but the simplest way to understand it is to just assume that we're flipping on the x-axis on one mirror and flipping on the y-axis on the other mirror. We can visualize the interference terms in this interferometer using the graphics shown here. Here we have the input field with the field at x equals 1, y equals 1. We flip it vertically, that x equals 1, y equals 1 is now down here. We flip it horizontally, and the minus 1 here has come over to here. So the interference between these 2 points is delta x equals 2 and delta y equals 2. Similarly, up here we'd have delta x equals minus 2 and delta y equals minus 2 for interfering these two. This would give us delta x is equal to 2, but delta x would be minus 2, delta y would be 2. And similarly, for every position where we take the field at the field that's been flipped vertically and the field that's been flipped horizontally and interfere them, we get a unique value of delta x, delta y. So this is implemented with the RSI instrument that was shown in the introduction. Here's a schematic of how this instrument looks. And for each value of x and y, we interfere and get a unique value of delta x, delta y, but we also have this term for delta x, delta y equals 0 from the self-interference of the two fields we're interfering. And then we can delay the relative path between the two arms as a function of delta to get a temporal delay. So we're now measuring the mutual coherence between these two fields for different values of delta x, delta y, and delta. So that can be analyzed then to recover the full cross-spectral density W of delta x, delta y, and nu by analyzing the Fourier transform of gamma with respect to delta. So for example, if you have a single point source, what you would see would be a cosinusoidal modulation. A single point source interfered with itself would create a cosinusoidal pattern. If you have 2 point sources, as is shown here, you see this kind of beat frequency between 2 different point sources. We know that if we take the Fourier transform of W of delta x, delta y with respect to space, we would recover the power spectral density for those 2 point sources. Shown on the previous slide, you take the spatial Fourier transform, a point, so a harmonic function corresponds to a point. When you take its Fourier transform, because there's 2 points, we see these 2 points. Now, we're actually measuring W plus the conjugate of W. So the conjugate beam in the lower quadrant gives us the inverse, or the flipped Fourier transform, because we've actually taken the cosine transform instead of the full Fourier transform. If you look at the RSI pattern you get from systems with finite spectral width, so instead of point sources at single frequencies, we have 2 point sources here with 2 different spectra. You see kind of the spectral envelope laid out, and then the 2 point sources have an orientation corresponding to their location in space that create these fringes in an RSI. So the RSI image in the end looks like something that's a cosine transform of the remote power spectral density of the source. You can analyze these terms because we've measured basically W of delta x, delta y on the RSI as a function of delta, and form spectral images of remote objects. And so that's the kind of thing that's shown here, that the RSI image you would see at a single frequency is a spatial pattern. This was done with a light bright toy, so you have a bunch of individual point sources making the CCI, as originally the Center for Computational Imaging. And by analyzing different frequencies as a function of path delay, you take the Fourier transform with respect to path, you get a spatial pattern. You can take its inverse Fourier transform and apply directly the Van Synter-Zernike theorem at optical frequencies to recover the image of the remote source. Now we know kind of the hard way, if we wanted to measure mutual coherence, it is possible to build interferometers that just directly measure W of delta x and delta y. They can be built in a variety of different instruments, but the RSI certainly is one of the more interesting and elegant ones. We've talked in each chapter about the kind of core problem in computational imaging, which is how to form images of remote multidimensional objects. We looked at projection tomography in the case of rays. We looked at diffraction tomography in the case of wave systems. In our next lecture, we'll talk about the use of these coherence measurements to form tomographic images, to create tomographic images of remote objects by analysis of the cross-spectral density. And that also could be done in a variety of ways. And ultimately, we'll talk about doing that with focal systems, where we can just use defocus and stereo matching to form three-dimensional images. But as a starting point, let's talk about coherence tomography, forming three-dimensional images by these coherence measurements. And to do that, we'll consider the use of an RSI for those systems. This might be the only example of a toy dinosaur that's ever been published in Science magazine, but it's a tomographic image as shown here that was reconstructed by measurements from an RSI. And we'll talk about how that works in our next episode.